All right, let's get started. This is part 1 of lecture 17, and it's about probability, and we're going to review some of the basic concept. So there's a few rules we're going to introduce, the rule of complements, the rule of sums, and the rule of products. So the motivation of studying probability is actually coming from Monty Hall. The story is if you have 3 doors to consider, and behind one door, for example, is a new car, and behind the other 2 doors, there is a lifetime supply of car wax. So you pick a door, but Monty does not open it. Instead, he opens one of the doors you did not pick to reveal it contains car wax. Now you can change your mind and choose the other closed door or stick with your current choice. So the question is, what is your best strategy and what is the probability that you will win? So hopefully, after learning about probability, you will be able to come up with the optimal strategy of this problem. So history of probability goes back to early 1600s. And it's originated actually from gambling. And it's coming from a question of how to split a pot from gambling. So the story is, would you rather play a game in which you win if you roll at least 1 6 in 4 rolls of 1 die, or a game in which you win if you roll at least 1 pair of 6 in 24 rolls of 2 dice? And the gambler lost a lot of money on his belief that the 2 games were equivalent. And eventually, Pascal and Fermat started investigating the problem. It was among the first serious investigations of the mathematics behind probability. And in early 1800, De Morgan said, probability as meaning the state of mind with respect to an assertion, a coming event, or any other matter on which absolute knowledge does not exist. But hopefully, we will learn some knowledge about probability today. So let's start with a simple experiment. You are going to see a lot of problems surrounding rolling the dice. So you have a pair of 6-sided dice, and where you're going to record the sum of the numbers that is faced up. So the first question is, how can we represent the rolls so that the outcomes are equally likely? One way to represent the outcome is to represent the outcome as a sum of numbers. For example, the sum of numbers goes between 2 to 12. When you have 2, that means you have 2 die, and then the 1 is on top, and the other one has 1 on top. So the sum is 2. Of course, when you get 2 of the 6, the sum is going to be 12. And then you can get sums between 2 and 12. The second version is you can represent as an unordered list with repetition. You can have, for example, double 1, double 2, double 3, and up to double 6. Or you can have 1 2, 1 3, 1 4, 1 5, 1 6, and so on. And keep in mind, this is unordered, which means basically 1 and 6 represent the outcome where one of the die is a 1 and another dice is a 6. The third way to represent it is using ordered pair. In this case, if you have a representation 1, 2, it means the first dice has a number of 1 and the second dice has a number of 2. And that's different from event 2, 1, where it says the first dice is 2 and the second dice is 1. So in this case, if you look at all possible events where order does matter, you have a total of 6 times 6, which is 36 number of possible outcomes. Okay. So when we study the mathematical probability, there is essentially two fundamental concepts which give you a probability of an event happening. The first is S, which corresponds to the sample space, which is a set of outcomes of the experiment. Okay, and then by default, we assume each of the outcome has an equal probability. And later on, we'll see examples where they don't have the equal probability. The second thing is the representation of E, which is a set of successful outcomes. Okay, and when we study probability, the probability of successful outcome is the number of instances in the successful outcome and number of instances in the sample space. In other words, the probability of the event is the size of the set of successful outcomes and the size of the sample space. Of course, this is better understood through examples. So before we go into examples, let's say a little bit more about sample space. Usually, we assume every single event in the sample space happens with equal probability. So they are equally likely to happen. If a single event is equally likely, then ordered tuples of these events will also be equally likely. Okay. And now the question is, what is the best way to represent the sample space for the dice experiment that we described before? But notice that not, if I have dice without ordering, then it's not true that all the orders or the tuples of those events are equally likely. So we'll see examples later. But now let's go back to our initial question, right? What is the probability of rolling a sum of 10 on a pair of 6-sided dice? That's the first question. The second question is, when drawing 2 cards from a deck of 52, so this is a deck of poker cards, so there's 52, and there's 4 patterns. And then what is the probability that 2 cards have the same value, either the same face or same number? Same face meaning that both of the cards are, say, king or queen, or they are of the same number. The strategy in both problems is first figure out what is the size of the space, the sample space. So what is n of S? And what is the size of the space of successful outcomes, which is a n of E? And again, the probability of the successful outcome is a number of the size of the successful set of size of the space of successes divided by the size of sample space. Okay, so this is a good time for you to pause the video and try to solve this problem on your own. Okay, and then we're going to do that in the we're going to do that after you resume the video. All right, let's look at the first question. What is the probability of rolling a sum of 10 on a pair of 6-sided dice, assuming each face has equal probability? So now, if I want to look at the probability, I need to decide the probability of my event is the size of my successful outcomes, the size of my sample space. So when you roll 2 dice, what is the cases where you have a sum of 10? You can have the first die to be a number 4, the second die of a number 6, or both of the die has a number 5, or the first one is 6, the second one is 4. Remember here, I'm treating the outcome as ordered pairs. So there's 3 possible ordered pairs with a sum of those numbers facing up a 10. So total, the number of successful event is 3. The second part is what is the size of my sample space. My sample space is all possible throw. As we seen before from here, if I have 2 dice, then if I'm looking at ordered pair, there's a total of 36 possibilities. Why? Is because for the first dice, you can choose between number 1 and 6. From a second dice, you can choose number from 1 and 6. So total, you have 6 times 6, which is 36. So now the probability of successful event for the first question is n of e over n of s, which is 3 over 36, which is 1 over 12. All right? Now the second question is asking what is the probability that two cards have the same value? So again, I need to figure out what is my probability of my event, which is defined over the number of successful outcome over the number of all possible outcomes. Okay. So first of all, let's figure out all possible outcomes. Remember, you are picking two cards from the deck of 52, right? And it's drawing card without replacement. What does that mean? That means in one way, when I pick the first card, I have 52 choices. Once I take that out, I want to choose the second card, and that has 51 choices. So that is 52 times 51. Of course, another way to write this formula is actually choosing 52 out of 52, which is P of 52 over 2, which is 52 factorial over 50 factorial, which is again 52 times 51. Record the formula. P of mn is equal to m factorial over m minus n factorial. Okay, this is applying for this formula. Now the second piece we need to figure out is what is the number of successful events. In this case, successful events is that if I have two cards that have the same value. Okay, so what did that mean really? When I try to figure out the two cards of the same value, I need to figure out what is n of e. Okay, so we can do the following. Let's say I pick a single card from the deck. And then how many other cards will match this card? Because there's 4 different patterns, right? So if I pick up one card, there's 3 other cards that will be able to match with it. Now, to choose the first card, I have 52 choices. So total, I have 52 times 3 possible cases such that the two cards have the same value. Okay, so now going back to the probability, this is number of successful event, which is 52 times 3, over all possible events, which is, or possible outcome, which is 52 minus times 51. And together, it's 3 over 51, which is 1 over 17. Okay, so let's dive a little bit deeper into the question of how do we actually arrive I'll move this later. Well, how do we actually arrive at, for this particular example, number of events is equal to 52 times 3. Let's think about this more carefully. I'm going to pick up 2 cards such that they match the value. Okay, so the way I'm going to do it, I'm going to divide it into 2 steps. Step 1 is pick the first card. And step 2 is pick a second card that matches the first card by value. So if my first card, I pick up, I don't know, a diamond 7, then the second card I can pick is maybe a 7, but in a different pattern, right? And total, there is 3 other patterns you can match it to, okay? So in step 1, when I pick up first card, I can pick any random card I want, and there's 52 cards to choose from. So the first step, I can choose 52 possibilities. I have 52 possibilities to choose the first card. So in step 1, I have 52 choices. Now, once I figure out the first card, I have 3 other cards that will match it by value. So in the second step, you have 3 choices. And in fact, what we're doing here is breaking down my sort of procedure into steps. And each step has some number of possibilities. And then you multiply them together to arrive at the final outcome. So together you have 52 times 3. That's the number of successful events. All right. Let's get back to this question again. So the rule of thumb is we're going to play with this formula, which is probability of E is equal to N of E over N of S. And we're going to use this multiple times. Okay. Now, I'm asking if I have a fair die that is rolled 3 times. The first question is, what is the probability that all 3 will give the same value? So for example, 1, 1, 1 is one of those successful outcomes. 6, 6, 6 is one of those successful outcomes. Okay. The second question is, what is the probability that a value comes up more than once? Okay. So this is a good time for you to pause the video and try to solve this on your own. And when you resume the video, we're going to solve this problem together. Okay, so let's look at the first question. A fair die is rolled 3 times. What is the probability that all 3 will give the same value? So again, the probability of an event is a successful event is a number of success outcomes over the number of all possible outcomes. So I just need to define what is, the sample space, size of the sample space. You roll a die 3 times. Okay, so you have 3 die here. Each of the die can choose from one of the 6 different numbers. So the first die have 6 choice number, the second has 6 choice, the third has 6 choice. So together it has 6 to the power of 3 choices. So that is the size of the sample space. Now, what is the size of the event space? We want to say all 3 rows will give the same value. So what are the possible events? It means all 3 rows have values, either 1, so all 3 1, or 3 2, 3 copies of 2, 3 copies of 3, 3 copies of 4, 3 copies of 5, and 3 copies of 6. So total, I have 6 possible successful outcome. So total, I have 6 over 6 to the power 3, which is 1 over 36. Okay. Now, for the second question, what is the probability that a value comes up more than once? Okay. So this is actually a little bit tricky to do. Essentially, you have to break down the cases. When a value comes up more than once, what are the scenarios? So possible scenarios. So I'm going to use the green to think about possible scenarios or possible cases. There's actually a few cases, right? It says more than once. So that means it's either twice or 3 times. So possible cases is a value shows up twice, or a value shows up 3 times. All right. So that's exactly how we solve this problem. The first step is we study a specific value that will comes up exactly twice. So a specific value come up exactly twice. It can come up, there's all 3 rows. It can come up exactly in the first 2 times, or the first time or the third time, or second time or the third time. So without specifying what value it is, total, I have 3 possible ways. So C of 3, choose 2. So among all those, they showed up twice exactly. Okay. So, and then the question is, what is the total number of possibilities? The total number of possibilities is this times 5. Okay. Why this is times 5? This is actually a very interesting question. Is because the one that does not occupy the space is already taking a value. So you have, for the remaining, you can choose among 5 of those values. Okay. Now, the second step is to say if any value that comes up exactly twice is, so the first step, you have a total of 15. And now you say any value that come up exactly once, exactly twice, this any value can be chosen among 6 different values. So you have 6 times 15, which is 90. So again, this is require a little bit thought into here. Again, let's go back to the situation. Why in the first step, I have 5. This 5 is actually looking at what values you can choose for the ones that is not repeating. And now this is choosing the value that is repeating, okay? And now the third step is any value that comes up exactly 3 times. So there are 6 possible values. So let's say 1 appears 3 times, 2 appears 3 times, 3 appears 3 times, and so on. So total, I have 6 numbers that appear 3 times. So now what's next? Now what I have is, if I asked step number 4, any value that comes up at least or more than once, it's going to be 90 plus 6, which is 96. So those are all successful events, which is 96. The all possible events or all possible outcome is 6 to the power of 3, as described before. Then the probability of the event is n of e over n of s, which is 96 over 6 to the power of 3, which is simplify 4 over 9, right? So now there is actually an easier way to determine the probability of the last example to consider the complement. So the question is, what is the probability a value comes up more than once? The complement of it is a value that does not show up at all, okay? So what do? Is we're counting, let's say E prime is the collection of all events with different values. So no values. So the previous one, a value comes up more than once. The opposite of, or the complement is the no values shows up more than once, okay? So no values show up more than once. So now I need to look at what is the possible cases. So the n of E prime is going to be, I have 6 possible number, and I choose 3 of them to show up in a unique way. So that's 6 factorial of 6 minus 3, which is 6 factorial over 3 factorial, which is 5 times 4 times 3, which is equal to 120. So the probability of the complementary event is n of E prime over the size of the sample space, which is 120 over 6 to the power of 3, which is 120 over 216, which is over 5 over 9. So now we're going to use the rule of complement, which is the probability of the actual event I care about is 1 minus the probability of its complement. So this is 1 over 5 over 9, which is 4 over 9. Okay. Okay. So that is a rule of complement. If I want to study the probability of the event E, E prime is a complement, so the non-occurrence of this event, then we can use the formula that probability of the event happening versus plus the probability of event not happening is equal to 1. Okay. Or in other words, the probability of event happening is 1 minus the probability of its complement. That's a rule we used in the previous question. So let's look at a sample example. We're asking if there is n number of people in a group, what is the probability that 2 or more people from the group have the same birthday? Okay, so the first question is asking what is the sample space and what is the size of the sample space? Okay, so what is the sample space? The sample space is there's n people. Let's say I'm using ordered list, and each of the people can choose among 365 days as their birthday. Let's assuming that there's only 365 days in a year for now. So S is essentially an ordered list of length n, and the values is drawn from the set that contains a number from 1 to 365. So what is a possible element in S? So let's say an element A is in S, right? Is that, it's stating what is the birthday of all the n people. For example, the first person's birthday is the 5th day of the year. Second person is the 11th day. The third is the 10th day. The fourth one is the 35th day, and so on and so forth. Okay. Now we are asking what is the size of the sample space? N of S. Because each person has 365 choices, and then you have total of n number of people in the group. Then you have 365 times 365, and you do this n times. Oh. N times, and then you get 365 to the power of n. So that is the size of my sample space. Now the question is, what is my E, and what is my E prime, and what is my the number of instances for unsuccessful event? Okay, so E is bigger or equal to 2 people have the same birthday. This is stated by the problem definition. Of course, E prime is now no 2 people have the same B day. Okay. Now, it's actually, for this problem, it's much easier to count the number of instances where no people have the same birthday. So what does that mean? That means I'm going to choose without replacement n numbers from 365. So that is P of 365 choose n, okay? Now the probability of E is 1 minus probability of E prime, which is 1 minus P of 365n over 365 to the nth power. All right, this is written down in detail in this slide. Let's look at a few more rules. So if I have two events that is mutually exclusive, meaning that they are disjoint, or it means that they cannot occur at the same time. If two events are mutually exclusive, then the probability of event 1 or event 2 occur is the probability of each of the event and add them together. The most important rule to use the rule of sums is to prove or at least understand the event 1 and event 2, they are mutually exclusive. Okay, that means it cannot happen at the same time. Let's give an example. If I now roll 2 dice and you need a sum of 5 to win. So you need a 5 to win. There's 2 events where you can get a 5. One, you can get a sum of 5. That is, you can roll a 1 and a 4, or 2 and 3, and you reverse order. So there's 4 different scenarios where the sum of the die is 5. Now, the second type of events where you get a 5 is 1 or more of the 5s shows up between the 2 rows. So maybe the first row is a number 1, the second one is a 5, or the first one is a 2, second one is a 5, and so on. You can enumerate all those possibilities. That is a second event. And you can see that the first set of events, E1, does not contain 5 in one of the row, while the second always contains a 1 in at least one of this row of the dice. So those 2 sets of events are actually mutually exclusive. So the probability of event 1 or event 2 occur is the probability of each individual event occurring. So in this case, probability of E1 is the total instances, n of E1 over n of S, which is 4 over 36. The probability of E2 is n of E2 over n of S. And that is 11 over 36. And I can add them together to obtain my final probability. Now, for any 2 type of events, E1, E2, and then I don't know whether they are mutually exclusive or not, then the probability of event 1 or event 2 occur is the probability of event 1 plus probability of event 2 minus the probability of event 1 and event 2. Of course, if E1 and E2 are mutually exclusive, then this minus term is actually 0. So it goes back to the previous rule. Okay. So there is a concept of independent events, is that 2 events are independent if the occurrence of one event is not influenced by the occurrence of the other. So in drawing cards from a deck of poker cards, there's always a concept of cards with replacement or without replacement. So if I'm asking you the probability of 2 kings, and I have 2 types of ways to draw the 2 king. One is I drew 1 card from the deck, I put it back, and I drew another card. The second type is I draw a card, put it aside, I have 51 cards left, and I drew a second card. The first case is drawing cards with replacement, and the second one is without replacement. And depends on which type you do, you get very different probabilities in this situation. So I would like to have this take home to see whether you can figure out the actual solution. If you cannot, or if you want to validate whether your answer is correct or not, please come to the office hour. So now we study the rule of product, okay? So if I have two independent events, then the probability of both events happening is actually given by the probability of them multiplying together. Because the outcome of the first event does not influence the outcome of the second one, or the outcome of the second one doesn't influence the outcome of the first one. So they are, right, again, the independence is by definition, two events are independent if the occurrence of one is not influenced by the occurrence of the other. So what is, I guess, one example is that, what is an example of independent events? Today is, well, hypothetically, today is sunny, and versus Netflix has a particular new show that is that they put on today online. So there's no direct causality between these two events. The occurrence of one event does not influence the occurrence of another event. So that's one example of independent events. So let's get the example. A die is rolled and a card is drawn. So a die, 6 faces, a card from a deck of 52 cards. What is the probability that the die and the card both show an even number? Okay, so there's two events. One is I get an even number on die roll, so that's E1. The second one, E2, is I got an even number on the card. But those two events don't, the occurrences of those events don't influence each other. So the probability of, both events happening is the probability of individual event happening. So we know that the probability of event 1, if you have a dice of 6 faces, 3 of them is even number, and the total number possible face row is 6, so you have 1/2. The probability of drawing an even number from a deck of cards is, again, how many even number do I have? Remember, I also have, cards that are not numbers. So in this case, you actually only have 20, you have 40 numbered card, but among them, only 20 of them are even number. So you have 20/52. Then finally, you multiply those together to obtain your final probability. Okay, so let's look at the last example problem. Again, you can pause the video and try to solve this on your own. Okay, so you have unfair die, sometimes it's called a loaded die, that the probability of getting a 6 is actually higher than any other number. It has a 1/2 probability. And then the rest of the numbers, say from 1, 2, 3, 4, and 5, each of those has a probability of 1/10. Okay. So the question is, what is the probability of rolling a 5 on the first toss and a 6 on the second toss? So what are the event? Event 1 is rolling a 5 on the first toss. And event 2 is rolling a 6 on the second toss. Okay? Then the probability of event 1 and event 2, those are independent event. So that's the probability of E1 times the probability of E2. So what's the probability of E1? It's rolling a 5. A 5 has a probability of 1/10. The probability of E2 is rolling a 6. And 6 has a probability of 1/2. So now this is 1/10 times 1/2, which is 1/20. Okay, so that's the last practice problem of this part of the lecture. And for part 2 of lecture 17, we're going to go over more practice problems regarding probability.